Right, so more of the further maths vector work. Could you just go back to look at how we go from the vector equation, point on the line, direction of a line, to the Cartesian equation in 3 dimensions with 1, 2, 3 elements. A special case would be, how do we cope with zeros in the vector equation, maybe? Well, if the zeros are in this part of the equation, the point on the line, we don't have to worry that much. We simply use exactly that rule, but we get x take nothing is just x over the 4 equal to y take 1 over the 5, and we get z take 2 over the 6. So a 0 here doesn't really cause us any problem. But also you'd have to recognise if you've got a Cartesian form with an element like that, it's implying there's a 0 here. Not much problem here. Where we have to be careful is we can't put zeros in denominators. So in this case here, we're okay to write y take 2 over 4. We're okay to write z take 3 over 5, but we can't divide by that 0. All we do is we put a comma and say that x is always 1. The x component of this is 1 plus nothing. The x is 1. So we get a Cartesian form that looks a bit like that. Right. Section 4 is the scalar product of two vectors, sometimes called the dot product because the symbol we use. It's not the vector or the cross product. When we multiply in scalars, 4 times 5 is 20. We have one definition for what a product is. We have one definition for multiplication. That is not going to be true for vectors. We're going to have a dot b, which is where we're going to have the product of two vectors, and we're going to get a scalar answer. We can also find, with a different definition, the product of two vectors and get a vector answer. That's going to be the vector product, and the symbol for that will be the cross we've used before. That explains why, at times in working on the board, I'll use the dot or the cross fairly lazily. In the vector work, it actually does make a difference. So, if you dot two vectors to get the scalar product, the answer is defined as being mod A multiplied by mod B cos theta. If we take two vectors and find the dot product, the answer is a scalar multiplied by a scalar multiplied by a scalar. The dot product is a scalar, and it depends on that length, and the angle between the two vectors. And we can give that a context, we can give a use for that later. In terms of how we actually work it out, we have, if vector A is A1, A2, A3, if vector B is B1, B2, B3, the dot product is calculated, dot product, scalar product, interchangeable. It's the sum of the products of these corresponding components. So it's the I components multiplied, the J components multiplied, and it's the K components multiplied. The product of those corresponding pairs, the sum of them. Okay? And notice a vector dotted with a vector gives a scalar answer. So, for example, if we took 1, 2, 3 and dotted it with 4, 5, 6. Oh, let's make it interesting having some negatives there. If I took that and found the scalar product of this and this, it is simply 1 times 4 added to minus 2 times 5 added to 3 times minus 6. 4 take 10 take 18 is minus 24. Two vectors giving a scalar answer. At this point, I'm not going to give any justification for why that and that give an identical answer. We can come to that. Let's get on first of all. I know you'll be impatient to know, and I know at least one of you with initials MQ will want to know right at the beginning. Be patient. Let's use it first of all and see about its applications. So, what can we use it for? We can find the product of two vectors now and get that, and depending on the context, this will be the appropriate product. If we know two vectors, we can now use this to find the angle between two vectors. So, for example, if I have a look at worked example 9.15, if we have two lines, 4, 1 minus 2 plus t 1 minus 1, 3. Oh, no, I'm going to mix things up a bit. In the book, it has them both in vector form. Let's do the other one in Cartesian form. So that's one line. If the second line was x take 4 over minus 1 equal to y take 1 over 4 equal to z plus 2 over 1. If I wanted the angle between these two lines, so we've got the first line might have a point 4, 1 minus 2 on it, and a direction of 1 minus 1, 3. The second line, they may or may not intersect. The second line goes through 4, 1, minus 2. Of course they intersect. Look, that and those match. So of course they intersect at that point there. And this one's got a direction of minus 1, 4, 1. If I want to know, let's turn that into a better diagram. If I want to know that angle that the two lines make with each other, I can, well, it's the directions which are going to define the angle, isn't it? You find the scalar product of the direction vectors. So that's 1, minus 1, 3, dotted with minus 1, 4, 1, which equals minus 1, minus 4, plus 3, equals minus 2. Minus 2 equals the modulus of 1 minus 1, 3, multiplied by the modulus of minus 1, 4, 1, multiplied by cosine of the angle between them. Okay, so minus 2. Now the modulus of that, square of the components, 1 squared, minus 1 squared, and 3 squared, so 1 plus 1 plus 9 is 11. So the modulus is root 11. 1 plus 1 is 2, plus 16 is root 18. Cos theta. Cosine of the angle between them is minus 2 over root 11, root root 18. So if we want that angle, theta is going to be shift cosine. Are we in degrees mode? Yes, we are. Shift cosine fraction -2 over root 11, come outside the root 18, close brackets, 98.2, and depending whether the question wants that angle or the acute angle, the acute angle is going to be 180. Take that answer, 81.8. Now, there will be times when we want one or the other of those, but for the moment we can practice using that. What uses can we put that to? Well, actually, no. We'll wait to do some mechanics before we put it to use. First use we could say is, because A dotted with B is mod A, mod B, cos theta. If theta is 90 degrees, if A and B are perpendicular, then cosine theta is cosine 90 is 0. If A and B are perpendicular, then A dotted with B is 0. If A dotted with B is 0, A and B are perpendicular. So it's a nice check for whether lines are perpendicular or not. They've got an example. They've got, let's work our way through this one. Prove that 2x plus 1 equals y plus 1. This is a worked example 9.18. Prove that this line is perpendicular to this line. Sorry, I stopped talking because I was reading there, didn't I? Right, I'll get back on it again. 2z takes 6 over 7. So this is worked example 9.18. Well, the first thing to say is they've done it nicely. They've changed the format, haven't they? Of, we've got a crazy format here, here, and here. So the first thing to do, if we want to work with this, if we want to prove they're perpendicular, it's going to be to do with the dot product of the direction vectors. So we need to show that scalar product uses dotted symbol because it's scalar answer. Scalar product of direction vectors is 0. So if we call this one line 1, equation of line 1, that needs to be an x plus or something. How do we do that? We can halve that value. So you need to halve the numerator and denominator. So we get x plus a half over a half is the same as that. Y plus 1 over 2. And equally I want z plus or minus something. I need to multiply top and bottom by minus 1. Z take 5 over minus 4. Those two things are exactly the same equation, but now it's in the proper format for the Cartesian form. L2 has form, so that one's fine. X take 2 over 4 is nothing wrong with writing a y take 0 over 6. And same here as I did there. I'm going to halve all those values. So z take 3 over half of that, 3.5, 7 over 2. How do I feel? I'm going to 3.5 think today. So direction of L1 is these three values. These three values, remember, give a point on the line. Direction of L1, half 2 minus 4. Direction of L2, 4, 6, 7 over 2. 4, 6, 3.5. Dot them. Half 2 minus 4 dotted with 4, 6, 3.5 is half of 4, 2 times 6, minus 4 times 3, what's that? 12 plus 2, 14, but it's negative, equals 0, conclude. Therefore, they are perpendicular. Okay. At this point, can I just show you something which is important? Let's say you didn't want to work with fractions. That's the direction. So anything which is a multiple of that is still parallel to it, isn't it? We could just have nicely have said, if we hate fractions, L1 is parallel to double all those. 1, 4, minus 8. L2 is parallel to double all those. 8, 12, 7. 1, 4, minus 8, dotted with 8, 12, 7 is 8, plus 48, take 56, equals 0. You can work with any multiple of the direction vector. Right, it's danger it might be a bit of a monster video again, but let's persist and get through the notes for this, and then we might have a bonus lesson where we just practice these ideas. The dot product has some applications in the mechanics which we're not looking at immediately. Let's cover the pure work first. One of the applications is finding the distance from a point to a line. Okay, how on earth is that related to the scalar product? And the book's got a good example. I'm going to use something similar, but before I do, I'm going to do the following. Imagine we've got a line and we've got a point, okay? So we've got a line whose equation is r equals a plus lambda b, and we've got a point which just has coordinates x, y, z. If we want the shortest distance of that point from that line, well, we've got, in terms of distance from the line, we could say that's the distance, we could say that's the distance, we could say that's the distance. But the shortest distance is going to be when that is at right angles. Okay, oh, that hasn't looked very much. I'm looking at an angle to it, sorry. So the shortest distance we're looking for is when the line connecting the point to this line is perpendicular. We're going to make use of that fact that the shortest distance is the perpendicular distance is what we're going to make use of in order to use the scalar product. Shortest distance from a point to a line is the perpendicular distance. How does that help us? Right, if we work our way through worked example 9.19, if we had line with equation 3 minus 1, 0 plus lambda 1 minus 1, 1 and a point A 3, 9 minus 2. So we've got this line 3 minus 1, 0 is a point on the line and it's parallel to 1 minus 1, 1. We've got a point A whose coordinates are 3, 9 minus 2. We want this distance here. How do we find it? We first of all find that point by making use of the fact that equation of B, a point, so coordinates of B, a point on the line, are 3 plus lambda. So we don't know the value of lambda. We're going to use the general form of this. Minus 1 take lambda, 0 plus lambda. Okay? Coordinates of B are that. We want the value of B, the value of lambda such that A to B is perpendicular to that line there. So perpendicular to the 1 minus 1, 1. A to B, to get from A to B, we take this off that. We do 3 plus lambda minus 1 take lambda, lambda, take 3, take 9, plus 2. Why on earth do we do that? If that's the origin, to get from A to B, we go from A to 0, negative of that, and then we go from O to B, which is what this position vector is. That gives us lambda minus 10 take lambda, lambda plus 2. We want the value of lambda so that this is perpendicular to that. So when is AB dotted with 1 minus 1, 1 equal to 0. Lambda minus 10 take lambda, lambda plus 2, dotted with 1 minus 1, 1, is lambda plus 10, sorry, multiply them. I started just thinking in my head there, didn't I? So lambda times 1, minus 1 times both of those, 1 times that, lambda plus 2. So that becomes, I'm going to move that page that goes along, 3 lambda plus 3 lambda plus 12. 3 lambda plus 12 is 0. Lambda is minus 4. So what? Why is that important? That tells us where B is. Coordinates of B are up to here now. 3 plus minus 4, so that's minus 1. Minus 1 take minus 4. 3 minus 4. Okay? Or, I'll take that out the variance order. Or, remember what we're trying to do. If one question was find the coordinates of that point, we've done it. If I want the length of this line, I want the length of AB. So, A to B was, A to B was that thing there, wasn't it? So I'm just going to write that again. Lambda minus lambda take 10, lambda plus 2. So, when lambda is minus 4, AB is minus 4, minus 4 take 10 is minus 6, minus 4 plus 2 is minus 2. Why on earth are we doing that? We want the length of that line. I want the length of that line when AB is perpendicular to that line. When these two things are perpendicular, B has that value, AB has this value. The length of that, the length of minus 4 minus 6 minus 2 is the shortest distance between the 2 points. The square root of 16 and 36 and 4, 40, 50, split 6, the square root of 56, 4 14s, 2 root 14, is the shortest distance of point A from that line. That was worked example 9.19. That's worth getting your head round. Right, that's now half an hour. I'm going to save that and then we can worry about distance between lines, okay? That's for another lesson.